All right, we should get started. Today we have the pleasure of having Nicole Halpern, who's a grad student at the Presco group, talk about some interesting work she's been doing on small-scale thermodynamics. With that said, Nicole.
Should we close the door?
Sure.
Well, thanks for the introduction, and thank you everyone for coming to a talk that has probably too long a title. This seminar starts with a story of a seminar from actually a year and 11 months ago. I was giving a talk about these two quantities. They're models for small scale, whatever that means, thermodynamics and statistical mechanics. The thermodynamic resource theories form a set of models for these systems, and one-shot information theory is a mathematical toolkit applied to these models. I was giving this rather abstract, mathematical, pure quantum information sort of a talk. It was probably the wrong topic because the crowd consisted of condensed matter and optics theorists and experimentalists. There's something of a mismatch. At the end of the talk, a friend of mine stood up and said, "You've given this very theoretical talk. This here is an experimentalist, so he's your worst enemy. He will want to know what anything that you just said has to do with what's actually going on in his lab. How will he see it? How will it affect him, or will it not?" And you had a couple of slides about motivations and technological possibilities, but I want to know details about that. So I said something about how these theories are very new, they're just being developed, there's a lot of way to go till experiments, although there's some inspirations and motivations, but he had a good point. So his questions have been burning in my mind for the past year and 11 months. I wanted to know, do these theories have anything to say about our physical reality? Are they observable? One of the motivations for this work is experimental advances. I'll talk a little bit more about those. I wanted to know, is there a connection? That led me to write this paper this past summer. So if you're interested in what's being said in the talk, then you can go here for details. Unfortunately, this talk won't be technical enough for the theorists, and it won't be physical enough for the experimentalists. So I probably won't exactly please anyone. However, I think that there are a few useful things that I can offer. One is I can offer an introduction to these models and to this mathematical toolkit and how it's applied in these models. I said that it might be a good idea to try to bridge the gap between this theory and physical reality. I'll discuss what needs physically realizing. I'll argue that now is the time to physically realize these theories. I'll present a few steps for moving across the bridge, but a lot more needs to be done. Perhaps you can help me with that. So yeah, I want to provide you with a little introduction so that we can start a conversation. First, I'd like to talk about the resource theory framework. It's a toolkit that's applied in quantum information theory. So every one of us has some idea of what a resource is. A resource is something valuable. Things are valuable when they're scarce. For example, we're in California, water is very scarce. It is a resource, it is valuable. Different things are valuable in different contexts. But whenever there are restrictions, then the resource theory framework might be a useful tool. These were, as I said, developed in quantum information theory. Perhaps the most famous example is the resource theory of pure bipartite entanglement, which is a very long name, so I will call it entanglement theory for short. When we use a resource theory, we have in mind some agent, some maybe experimentalist, who has certain tools and certain skills. Using these tools and skills, the agent creates and manipulates quantum states. For example, the tools might be local operations and classical communication. But maybe your agent can perform some Pauli operation on a qubit that he or she has, him or herself, and can also send information down a telephone wire to Alice or Bob. Those are LOCC, the allowed operations in the entanglement theory. When we use a resource theory, we think about transformations between states. Which states rho can transform into which state sigma, which states cannot transform into which states, how much of this can you turn into how much of that, what is possible and what is impossible. There are three very closely intertwined properties that characterize a resource theory. One is this set of free operations that really defines the resource theory. One is the set of free states. One of the free operations is the ability to create from scratch any state of a particular sort. For instance, in the entanglement theory, we might be modeling someone who a while ago had a lot of trouble creating controlled entanglement in a lab. We would approximate this person as able to create, in contrast, as many unentangled states, separable states, as he or she wants. Those are free in this approximation. Any state that is not free is a resource. It can't be created from scratch, though it's valuable. Though our agent might not be able to create an entangled state, but maybe a friend from the lab down the hall can create such a state and loan it to our agent. For example, in the entanglement theory, entangled states are valuable. So if you have a bell pair, a maximally entangled state, you can use it along with LOCC to simulate a quantum channel. One set of resource theories is the set of thermodynamic resource theories, or I'll talk about one in particular. These are models for, again, small scale, whatever small scale means, or general, non-equilibrium and equilibrium statistical mechanics. So these model interactions between systems and mass. These are a couple of the earlier foundational papers in the fields. They actually came out a few years earlier than 2013. That's when they were published in journals. But over the past few years, the literature has exploded. I have not been able to keep up with it. It's run away recently. That's one of the reasons why I think that now is the time to realize them physically. A whole lot of theorems have been built up. They're lovely theorems, but what do they tell us? There are a couple of reasons to study thermodynamic resource theories. This is one of the papers that I mentioned on the last slide, Fundamental Limitations for Quantum and Nanoscale Thermodynamics. People might want to know about what is ultimately fundamentally possible. These resource theories are very simple models. That means that they're mathematically easy to use. They are probably difficult to implement because they model an agent who has a great deal of control that might be unrealistic. But we might ask, suppose that you had a ton of control. Then what are the ultimate limits on what you can physically do? That's worth studying. There are also some technological motivations. Here's a hand-wavy sort of picture about how this framework fits into statistical mechanics. With ordinary statistical mechanics, we model large numbers of particles. But in experiments nowadays, people can control very small systems, single molecules. In some of these systems, thermodynamic and statistical mechanical concepts, such as work, heat, and entropy, remain relevant. How do we put together these statistical mechanical concepts formulated in the context of many particles with, on the other hand, these very small systems? You might think that we need a new toolkit. This is a candidate toolkit. It sounds kind of reasonable, I think, but when you try very hard to see exactly how the two fit together, it's not entirely clear. I think that's one thing that needs clearing up now. Now is the time to find out, because there are all these platforms in which there are small-scale effects. There's a considerable amount of control. These are the systems that are inspirations for the theories, though I think it would be a good idea to figure out, are these theories relevant to these platforms as people would like to think? If so, we have even more reason to study the resource theory. If not, maybe we should devote our attention elsewhere. And also, if this is the right toolkit for these platforms, we should be using it. We, who knows, might be able to make some technological process or understand these systems better. For example, these are hairpins. I'll mention them a lot later in the talk. People stretch and compress single molecules of DNA. They can measure the amount of work required to stretch this DNA loop a little bit. That's how work is relevant in these contexts. Or some very interesting work by Yuka Piccolo's group involves single electron boxes, and there they talk a lot about the work and the heat. They also have observed similar but different models for small-scale statistical mechanics. Suppose that I have sold you on this idea, you love the resource theory framework, and now you want to use it to model your favorite system. How do you do it? Each system, each physical system, is associated with some Hilbert space. Defined on that Hilbert space is a density matrix rho and a Hamiltonian H. We assume that the agent is given access to some giant heat bath at some fixed temperature T. Usually a heat bath, we can think about more general baths as well. We assume that from the heat bath, the agent can draw any Gibbs state that he or she wants. He or she can dream up a Hamiltonian, H sub B, and create this thermal state. There's a star here because usually we assume that the Hamiltonian spectrum is bounded and discrete. For simplicity, for mathematical convenience, that might not be so realistic. If so, that's another opportunity to bring these theories closer to experiment. Why should these states be the free states? Well, there are two reasons. One is a mathematical reason I won't go into here. And the other reason is, suppose that you have some heat engine. You have some giant temperature T bath, and you have a non-equilibrium state. You have a very cold bath as well. Suppose that you allow the cold bath to equilibrate with a large hot bath, then you can, using an engine, extract work. Work is valuable. The work comes out of the non-equilibrium state. It sort of makes sense that non-equilibrium states have value. It sort of makes sense that equilibrium states, Gibbs states, would be worthless. They should be free, they should be easy to create. What are the free operations that define these theories? They tend to bring states farther down toward equilibrium. Each free operation consists of 3 steps. The agent can tensor on any Gibbs state. The agent can transform the composite with any unitary that preserves the whole Hamiltonian. This implements energy conservation or the first law of thermodynamics. The agent can throw away any subsystem. But mathematically, each free operation looks like this. The agent starts out with some state, maybe this is a state that the friend from down the hall created and loaned our agent, some state rho. The agent can tensor on a Gibbs state, can transform with some unitary. That unitary has to conserve the total Hamiltonian. And to clarify, this is what I mean by the total Hamiltonian. So this unitary performs some interaction between the system of interest and the bath system. The agent can discard a subsystem. These are some of the questions that I would like to answer.
So the Hamiltonian you're assuming is just the system Hamiltonian plus bath Hamiltonian, but not an interaction term when you're computing the energy.
Right, the unitary implements the interaction.
Okay, but it doesn't come into the energy when because energy,
Right.
Normally you think energy conservation involves H system plus H bath plus H system there.
Yes. So in this case, no, the Hamiltonian has this simple form and the unitary has to preserve the Hamiltonian. But it could be that the operation that you're performing involves introducing some extra energy in the system, and in that case, you could just have an even larger Hamiltonian for system plus bath plus battery, that's your source of energy, and the unitary would preserve that total energy.
Is there some specific, but it seems like a quite restricted limitation of the
That it conserves the total energy?
Yes.
Yes.
So
It's,
is there something in mind, like time evolution and that important, or?
yes, so my answer to that would have at least 2 parts to it. One is, well, first you asked about time evolution. Yes, that's important. I believe that time evolution commutes with all of these, time evolution commutes with the free operations. And as I'll mention later, a lot of the results in this resource theory are quasi-classical. They're about states that commute with their Hamiltonians. We assume all of the operators commute because that's mathematically simple. That's the context in which a lot of these results are derived. But then we can consider coherences relative to the energy eigenbasis, and then time evolution becomes more of a problem. And that is something we actually heard a seminar about during this past summer by Matteo Bastaglio. He thought a lot about coherence in the context of this, and that's when time evolution becomes very relevant. But in this case, the time evolution ends up commuting with the free operations. And the reason that we suppose that the unitary conserves the total Hamiltonian is we just think anytime you model the system with a sufficiently large model, then that is a closed system, an isolated system, and so its energy must be constant. If its energy isn't actually constant, then we can just include the change in energy system into our model so that there's this bigger model, and on the bigger model, that energy is conserved.
So in some sense, U is action by some parts in the system. I don't know.
It's what, sorry?
By act, U is like by acting by what is already present in the system. So I don't know.
Yeah, these are supposed to sort of model thermalization. Then, for example, they preserve Gibbs states, and they tend to bring states. So they'll either preserve the distance between your state of interest and the Gibbs state, or they will decrease that distance. So they sort of model thermalization.
So let's think of two harmonic oscillator. One is in some arbitrary state, the other is in a thermal state. Could you tell me what is the U that here you are using now this that can transfer energy between these two? Give an example.
Suppose that you had a qubit row, and suppose that you had a bath qubit. Suppose that they have the same gap. Then if you put them together, then there's one degenerate energy level, and you can permute the states within that degenerate energy level because it conserves the total energy. And that's just a simple example of one of the unitaries.
Does this model also allow for, say, drawing like multiple uncorrelated free states from the bath all in like a single step? Because generically, like a product state of thermal states, all with the same Hamiltonian HB, is not necessarily going to be the same as like a thermal state of the entire like composite.
Yeah.
system with multiple.
So suppose that you're interested in drawing a thermal state with Hamiltonian H1, a thermal state with Hamiltonian H2, and so on. That entire large state is itself a Gibbs state. So you can just say, I have defined a Gibbs state on H very, very large. That's what my agent draws from the bath, and it just so happens that this H large factorizes into a whole bunch of small h's, and so your total Gibbs state factorizes into a whole bunch of small Gibbs states.
Okay. So this is presuming that there are no like, interactions to begin with, like between the systems that you draw. Or I guess that you can't like draw. It's like part of interacting.
You can draw any Gibbs state from the bath, and Gibbs state times Gibbs state is another Gibbs state. That's also sort of related to one of the reasons why the Gibbs states are free, but that has a whole lot of detail behind it, and we can talk about it later. So I mentioned, so we define the model. Why study it? One reason is that, and these questions might become clearer in the near future, but one of the ideas is that since we have control over these small scales that are supposedly no longer described by ordinary statistical mechanics, this resource theory tool is really needed. It would be nice, I think, to check that and see whether it is applicable and can provide new insights into the supposed inspiration for this model. One tool that's applied in these resource theories is one-shot information theory. This is a mathematical toolkit. It can describe systems that are not described by the sort of statistics that we apply in, let's say, Physics 127. The beginnings of this theory appeared a few decades ago, but it's been also booming in the past few years. It's especially been taken over by the quantum information community. There are people all over the world working on this, including some of the people at Caltech. I don't develop so much this mathematical toolkit, I just like to apply it, but there are people around who will tell you a lot more detail about it than I can. This mathematical toolkit has a lot of applications. For example, to information processing tasks like data compression, channel capacities, quantum cryptography, quantum key distribution. One of the applications that's cropped up recently is thermodynamics. To see how it has been applied, stick around for part 2.
So we'll take a short 15-minute coffee break, and then we'll come right back. It's on the next room over there.
Back to one-shot information theory. We're more familiar with Shannon theory, the ordinary brand of information theory. Suppose that you have many copies of a random variable x, or for quantum people, many copies of a density operator rho. Later I'm going to be often using quantum notation. This is an IQIM Seminar, but a lot of the results can be used for classical systems or quantum systems. Take your pick. Suppose that you have many, many, many copies of this random variable or density operator. Suppose that you take the limit as n approaches infinity. This is called the asymptotic limit. That is what is described by Shannon theory. Suppose that you simultaneously process all of these copies, perform some information processing task. With what efficiency can we perform that task? That is the study of Shannon theory. For example, we can think of data compression, which some of you might be familiar with. Suppose that the random variable x is some letter in a possible alphabet. There are many possible values, x of 1, x of 2 of the letter. The probability that the letter x, the random variable x, assumes the value x of 1 is given by p sub 1, and so on and so forth. Suppose that we take many, many, many copies of this random variable x. That forms our total message m. Then we take this asymptotic limit. Suppose that I want to send you this message, but I don't want to send you a very, very large package. So into how few bits, how few units of information can I compress my message? The answer is given by the Shannon entropy of our original distribution. Shannon entropy is defined like this in terms of the original probabilities. That's the number of bits per copy of the random variable needed. There's a somewhat similar story in statistical mechanics, though it goes a little differently. Consider some system. It has an energy. This is a random variable. It's in one of many possible microstates labeled by I. Each microstate is associated with some energy. What is the probability that the system has some particular energy, is in some particular microstate associated with some particular energy? That's given by p sub I. One particularly useful p sub I in statistical mechanics is the Gibbs distribution. We can define the Gibbs entropy in a statistical mechanical setting like this. We take the Shannon entropy and stick a dimensionful factor out front. Not everyone likes this formula, but it's used pretty widely, so I'm just going to go with it. Just as we talked about an information processing task earlier, we can talk about a thermodynamic task. Here's one example. Suppose that you start off with a physicist's favorite system, a gas in a box. The gas might interact via some thermal coupling with a bath at some fixed temperature T. Suppose that the gas starts at equilibrium and you compress it very, very slowly, quasi-statically, so it always stays in equilibrium. How much work do you have to perform to compress the gas? That is our measure of efficiency. The answer is given in terms of the difference in Helmholtz-free energies between the initial and final states. That is given in terms of an entropy. You can also express this in terms of a relative entropy, so even more entropies. Note that the reverse process has the same efficiency. Suppose that you let the gas expand slowly, and you ask, how much work can you extract from the molecules that are bouncing off the pistons? The answer is the same, delta F. Now, this reversibility is characteristic of ordinary statistical mechanics, which involves some sort of averaging. But in the resource theory framework and the single shot framework, we'll see that these two analogs of these two efficiencies differ from each other. That's one of the interesting results of this resource theory framework. However, from those results, you can recover something that looks a lot like this. But we were talking about data compression. There is a quantum version of the data compression problem, just again for the actual Q people in IQIM. Suppose that your message consists of many, many, many copies of a density operator rho. Suppose we take the asymptotic limits into how many qubits, quantum units of information, can I compress the message? I need a number of qubits given by the von Neumann entropy, which is a generalization of the Shannon entropy. This is applicable to the limits as n approaches infinity. Now, I don't know about you, but I never have n approaches infinity copies of anything. That's why we use one-shot information theory. I'm sure that everyone in this room is a rabid fan of Eminem, the rapper. But as he says, sometimes we don't have n approaches infinity copies of a density operator or a random variable. Sometimes you only get one shot. Do not miss your chance to blow because this opportunity comes once in a lifetime, y'all. How do we follow the advice of our distinguished friend, Eminem? We use one-shot information theory, and this is a toolkit that describes the efficiency with which we can quantify the efficiency with which we can perform information processing tasks if we have an arbitrary number of copies of quantum state or random variable, including just one copy of a random state, or 50, including one shot. We saw that entropies, the Shannon entropy and von Neumann entropy, play important roles in Shannon theory and quantum Shannon theory. A whole zoo of entropies appears in one-shot information theory. I'll introduce a particularly simple family of quantities, the order alpha Renyi entropy. This is the definition. Here, alpha is some parameter. It usually runs between 0 and infinity. Sometimes negative values are relevant, sometimes we can ignore them. This definition might look a little strange, but there's a log here, and logs tend to show up in entropies, so that's sort of comforting. I'm going to talk about 3 of the Renyi entropies that show up a great deal in these one-shot thermodynamic resource theories. One example is the order 1 Renyi entropy. Suppose that we take the limit as alpha approaches 1. Then this quantity here approaches either the Shannon entropy or the von Neumann entropy in that limit. So this generalization really is a generalization, and in a special case it reduces to something we know and love. Another important Renyi entropy is the order 0 Renyi entropy. Sometimes nowadays the order 1/2 Renyi entropy is called the max entropy, but it doesn't really matter here. Suppose that your quantum state rho is defined on some Hilbert space, and the dimension of the support, the number of non-zero eigenvalues of your density operator, is this number, dimension of support of rho. The log of that is the entropy. Or if you're a classical person and you're interested more in probability distributions, then you would consider the number of non-zero elements in your probability distribution. That's the argument. We talked about data compression earlier and the asymptotic limits. Suppose that you're interested in some arbitrary number of copies of rho, then the efficiency with which you can compress is given by the max entropy. Or in thermodynamic resource theories, the efficiency that's quantified by this entropy is the amount of work extractable from some non-equilibrium state. When I say work extractable, I'm thinking about some process. I'll talk about it more in detail later, but it's sort of the analog of starting out with some compressed gas and allowing it to expand so you can extract work. There's also the mid-entropy, or the order infinity Renyi entropy. Suppose that Pmax is the greatest eigenvalue of your quantum state rho, or for classical people, the greatest element in your probability distribution. That's what goes here. An information processing task whose efficiency is quantified by this entropy is randomness extraction. Suppose I give you a bunch of copies of some not exactly uniform distribution, just some probability distribution. You would like to extract from it a uniform distribution. How come? Random number generators are useful. Sometimes we want some source of pure or almost pure randomness. This quantifies the efficiency with which we can perform that task. In thermodynamic resource theories, think about the reverse of the process that I mentioned on the previous slide. So consider creating some non-equilibrium state, some valuable state. You need a source of value, a source of work. This is analogous to compressing the gas. So how much work do you need to perform to compress a gas, create this state? That's given by the min entropy, in contrast to the max entropy, which quantifies the reverse of this process. Again, things are a little different in the one-shot scenario than in the asymptotic conventional scenario. Let's compare and contrast the role of information theory and entropy in ordinary statistical mechanics and in the setting we're talking about here. In ordinary conventional statistical mechanics, the Shannon entropy governs the efficiencies with which you can perform transformations. For instance, we said work cost of formation equals the work extractable. Both of those are given by the same entropy. So suppose that you ask if some process can occur spontaneously. You might say, this is some hypothesized process. Does it really occur? Can it occur? Then I would say, well, check the entropy of the original state. Check the entropy of the final state. Does the entropy increase monotonically? Then we're more likely to expect to observe the process. But in thermodynamic resource theories, different entropies are relevant to different processes. For instance, we said that the different Renyi entropies quantify different work processes. And we can ask a similar question about sort of spontaneous processes in the resource theory framework. We said that free operations tend to thermalize states. So we might ask, suppose that your friend from down the hall loans me this state rho comma h. Suppose that I'm interested in seeing whether it can turn into sigma comma h prime by free operations. Then you might think, oh, we should just look at the entropies of the state, or the free energies. In fact, we have to check a whole bunch of functions, a whole bunch of entropies, and see if they decrease monotonically. So the restrictions here are more fine-grained. But in the limit in which you take a whole lot of copies and take some average, then we get back just one entropy, although I haven't shown you how. So suppose that we want to observe somehow, or physically realize one-shot thermodynamic resource theory results. What would we look for? We might look for Renyi entropies that differ a great deal from each other and from the Shannon entropy, and in particular that have non-zero values. Here's one example of such a state. You can think of it as an L-shaped distribution. So consider this probability distribution. Suppose that there are d possible events. Here's one event, here are d minus 1 events. There's one very large, very probable event, and there are a whole lot of events that have a very low probability. You can visualize the probability distribution like this. So here's the 1/2, here are a bunch of very improbable events. This forms an L shape, hence the name. We can calculate the two entropies of interest. We said that the order infinity Renyi entropy is given by the greatest probability in the distribution. That's 1/2. This entropy equals 1. We said that the order 0 Renyi entropy is given by the number of non-zero eigenvalues. That's d. D can be very large if there are many, many possible events. So these entropies differ a great deal from each other. So we'd expect to observe the effects of the discrepancy between these rates that we talked about in the resource theory framework. This is what we might want to observe. How do they manifest in the resource theory framework? Well, we just talked about work cost and work extractable. Also, I mentioned these second laws for transformations. Suppose that your state, rho, is block diagonal relative to the energy eigenbases. Suppose that all the states commute with their operators, and everything is relatively classical. It's relatively easy to deal with. A lot of results in the resource theory framework have this form. These problems were solved earlier. There are some really interesting results here, and they are applicable to some classical problems, quasi-classical problems. Then, after solving those problems, people add coherences on top. If you want to check whether rho comma h can transform into sigma comma h prime, you have to check all of these second laws, if there are no coherences. If there are coherences, then you have to check yet another set of second laws. We don't even have necessary and sufficient conditions for these transformations. That's still an open problem. I'd like to walk you through an example of a resource theory problem. It's not one that I came up with. It's in one of these foundational papers. but I think that it would be useful to walk through what one of these problems looks like. What does a system of interest look like? Suppose that an agent has in mind some state, rho comma h. The agent would like to create this state using free operations. The agent has a friend who says, I'll give you a battery full of work that you can use to create this valuable non-equilibrium state if you tell me how much work you need. How high should I charge the battery? That's what the agent wants to do. But the agent says, no, I wouldn't mind creating some state that's very, very close to the state that I want. I'll create some state that has the same Hamiltonian, but the density operator is, let's say, within trace distance, epsilon, of the desired state. So the agent might ask, what is the least amount of work that I will need to get from my friend to create any such state? This is how I'm going to denote that quantity. I haven't actually defined work. I've been using it a great deal throughout the talk, but I haven't defined it in the resource theory framework. We can start to fix that problem. There are a number of different models for work. One involves the work bit, sometimes called the WIT for short, very wittily, I'm sure. I did not come up with the term. We suppose that there is some system that is a two-level system. It has energies 0 and W for some particular W that we have to calculate. We assume that the battery is always in some energy eigenstates, E, where E can assume any one of these two values. This is probably not a very realistic model. I've been told by quantum dot people, no, we cannot engineer a Hamiltonian that looks just like that. That's a little bit of a problem. Supposedly, this is equivalent to a number of other battery models, but this is one of the steps that might need to be taken to bring these theories closer to physical reality. And it's easy to calculate with. This is the question that we want to answer. Let me phrase it a little bit more mathematically rigorously. We want to calculate some W, right? Which W? The W such that if we start with a charged battery, we can tensor on some bath state. We can perform some unitary that conserves the total Hamiltonian. We can discard the subsystem. Sorry, actually, as I was talking with some other people about recently, we could actually add another term to this Hamiltonian that incorporates the Hamiltonian of the battery. That should be in there as well. So anyway, the composite system energy is conserved, so we can throw away some subsystem and end up with a state that is epsilon close to the state that we wanted to create. What is that W? I won't go through the derivation. I'll just give you something that's very similar to the results. Suppose we're interested in creating a state. This expression isn't actually correct. Anyone familiar with this resource theory result knows that it's wrong, but it's very similar, and it involves the entropies that we know. I didn't want to introduce even more entropies. I mean, out here, there's some dimensionful energy factor. Here is the log of the dimension of the space on which our state of interest is defined. Here we subtract off some entropy. We saw H infinity is one of the Renyi entropies. This epsilon here is some generalization that's been defined by the one-shot community and incorporates this error tolerance. That's the work cost. Now suppose that we ask something very similar to the reverse question. We say, suppose that you start off with a state rho comma h, and you want to extract work from it to raise that battery to a high level. Well, actually some state that's epsilon close to a pure state W, to a pure energy state W. What is the greatest W for which we can do that? Here's that answer. It's similar to asking how much work is required to compress a gas. Or sorry, how much work can you extract from allowing a gas to expand? So the form of this expression is very similar. We have a dimensionful energy factor, we have a log, and we subtract off an entropy. But this is a different entropy. So in this framework, these processes are given by different efficiencies quantified by different entropies. However, we can take a limit in which there are many, many, many copies. We can take some average, and we can get back the results that we might expect from our ordinary conventional statistical mechanical intuitions. could either go through this or skip it. Who's feeling particularly tired? Does that mean I should?
Can we go back one slide quickly before we answer that? So it seems that you can extract a lot of work if the dimension of rho of your density matrix is really, really large, right?
So there are a few different qualities that a state would have that would enable you to extract a lot of work from it. So suppose that your state is a pure state on a very high energy level, then you can extract a lot of work from it. Suppose it's a pure state, and yes, having a large system and maybe a pure state on that large system is associated with a lot of value. And that can be seen especially in the resource theory. That's a very simple case of this more general thermodynamic resource theory in which all the Hamiltonians are zero. And there's a paper about that theory in which the importance of the dimension of the space is brought out explicitly. Okay. I'll go through this. Hopefully it won't be too bad. There's only one slide of something that has maybe too many equations on it. Suppose we take the asymptotic limits. We ask, as we asked in the data compression example, how much of a resource, how much work is required or extractable per copy of the state. So we are interested in the work cost or the work extractable. We take n copies of our system, so n rho tensor to n, or Hamiltonian plus Hamiltonian and so on, n terms. Then we take this average, 1 over n. Then we take the asymptotic limit. In the asymptotic limit, these quantities approach each other. We use a mathematical tool that's an asymptotic equipartition theorem, which also has far too many syllables. We find that both these quantities approach a dimensional energy factor times a relative entropy. The relative entropy is between the state of interest and the Gibbs state over that Hamiltonian. And we know the definition of the relative entropy. We can just substitute in. Gamma in this case is going to be this equilibrium state. We can do some algebra, and then we can do some more algebra, and we end up with this result. It's actually relatively easy to parse, because this here is an average energy. This is a temperature, and this is an entropy. This here looks very similar to the Helmholtz free energy that we talked about earlier. This, in fact, is the Helmholtz free energy of the canonical ensemble. So in the asymptotic limits, the work required, or the work extractable per copy, approaches something that looks like a difference between Helmholtz free energies. We talked about that way at the beginning of the talk when we were talking about ordinary, conventional, statistical mechanics, or thermodynamics. These resource theory results tell us something about this one-shot limit that we can't get from ordinary statistical mechanics, but it also gives back results that we would expect, which I think is nice about the resource theory framework. I mentioned that now is the time to try to physically realize these models. What are some of the questions that we should ask? I approached this question from very much a theorist's perspective. I do not have a ton of experience with experimental systems. That's something that maybe people here can help me with. But I know some of the questions that need asking. On the following slides, I'm going to have an E and a T. This is a question for the experimentalists, and this is a question or a challenge for the theorists. First, the resource theory framework was developed in part to model what happens in a lab, to model what people can do easily. Again, at some time, in some places, people could not create controlled entanglement easily. That's one reason for coming up with the entanglement theory, although not the only reason. So thermodynamics was developed by people who were interested in what engineers could do with steam engines. We want to say something about real priorities and abilities. There are some priorities and abilities of resource theory agents that do or do not match with those of experimentalists. For instance, I was talking to Manuel Andres, who almost came but said he just couldn't make it here. Said, oh, supposedly in the resource theory framework, any unitary that conserves the total Hamiltonian is free. It's supposedly very easy to do. But a controlled many-body unitary is not necessarily easy to perform. Said that the agent can pull from the bath. Pull from the bath any desired Gibbs states. That's not always possible. I'm going to talk about that in more detail. One point at which maybe the priorities intersect is coherent operations. So, thermal operations tend to bring states down toward the equilibrium state. They also tend to decrease coherences in a certain manner, quantified in part by Matteo Lostaglio, whom we heard from a few months ago at the seminar. Also, coherent operations, or increasing the coherence relative to a particular basis, might be more of a challenge in a lab. So these are some other challenges in which the two might disagree. For instance, when I told Manuel about the importance of work in this model, he said, "What work are you talking about?" So I talked about how, well, you use electric fields, right? And in order to increase the electric field strength, you have to bring a charge from far away over here, bring another charge over here, bring another charge over here. The charge builds up, so the electric field strength increases. Every time you bring a charge, you have to do work against the electric field you've already been up, you've already built up. So you are doing work. He said, "Yeah, I guess that's right, but I don't care. I don't care about how much work I drain from a battery." So maybe this isn't very realistic, even in some experimental setting in which thermodynamics is very important. He certainly deals a lot with thermodynamic and statistical mechanical ideas. On the other hand, people like Yuka Piccola can measure and think about work and heat. So should see what platforms are suitable and to what extent the model agrees with, or at least can be observed by experimentalists. This is a challenge for both parties. So experimentalists don't have exact control over the bath. In the resource theory framework, a lot of results depend on the ability to perform specific unitaries, but experimentalists cannot perform arbitrary energy conserving unitaries because not all of them are very easy. So we might want to see which ones are really possible and easy in which particular platforms. Also, we might want to coarsen the set of operations, assume that the agent doesn't have so many free unitaries. There are some people in London thinking about this problem, although it's not solved. Some of the systems that might be usable for testing these theories are condensed matter systems or quantum optic systems. For instance, we heard about optical mechanics last week. But the ideas seem relevant, so maybe those would be good systems. The natural language for describing some of those systems is quantum field theories. But quantum field theories haven't quite made their way into thermodynamic resource theories. I think that could actually be a rather fun theoretical problem to incorporate them. Some initial steps have been made, but not a whole lot of progress. So I said the agent can draw an arbitrary Gibbs state from the bath. And in particular, there's one very much relied on proof in resource theory papers in which the result becomes exact as the size of the bath grows infinitely large. Experimentalists do not have access to an infinitely large bath. Granted, this problem is not a problem solely of the resource theory framework. There are all sorts of statistical and mechanical problems in which we assume that the bath is infinitely large. In fact, it is not. So there are ways of dealing with this problem in other systems, and I think some people here are working on that. So those ideas should make their way into the resource theory framework. Or we should evaluate, are those corrections not so bothersome? There's a whole problem called the embezzlement problem. I won't give much detail now, but if Tejas opens the question and answer session with, are there any questions, and there's a really awkward silence, then here's a great opportunity to break the awkward silence. I hope that at least the name catches your attention, so you might want to ask more about it. It's a huge theoretical problem to some people, and it would be really cool if it could be realized experimentally, because it makes sense physically, but it's counterintuitive. There's a set of results called fluctuation theorems that were derived in non-equilibrium statistical mechanics. Some of the very important results we actually heard about in the colloquiate here last year. Crookes theorem, Jarzynski's equality. There are also some people in the room who have worked on these. describes systems that are very similar to the systems described by thermodynamic resource theories. They're small scale, they involve heat, work, and entropy. You can rederive, in a way, the second law. So there's a lot of overlap. But one benefit of fluctuation theorems is that they've been tested experimentally. Here are some of the platforms with which they have been tested. This is a single electron box that I mentioned earlier by IQIM group. I also mentioned the DNA hairpin earlier. This is a classical system. This is sort of effectively a classical system. These might be an opportunity to bridge thermodynamic resource theories to real physical reality via fluctuation theorems. Some progress has been made, but I do not know how to actually use these. So I think that's a really interesting problem. Some systems have continuous spectra. Again, last week we heard about optomechanics. When we talk about optomechanics, we often talk about some electromagnetic mode in a cavity. The mirrors at the end of the cavity might be leaky. So the mode in the cavity is coupled to the electromagnetic continuum outside. Continuum. I did say that the Hamiltonians that people tend to like to deal with in the resource theory framework have bounded discrete spectra because those are easy to deal with, but maybe they're not very realistic. We should have a conversation about how we might incorporate continua into the theory or whether it's not relevant for the right platforms. And there's the nature of some of the resource theory results. Some of the resource theory results are about optima. What is the most work you can extract? What is the least work required? We can't achieve optima in experiments. That's sort of a problem. So testing those results would be a little difficult. Can't test them directly. Then again, this isn't a problem solely with the resource theory framework. But people have come up with methods. For example, this is a graph from a paper by the Nicole group. They were testing Landauer's principle, how much work is required or how much heat is dissipated when one unit of information is erased. There's an ultimate limit called Landauer's principle on the amount of work or amount of heat. That limit is achieved in the quasi-static limits as the process is performed very, very, very slowly. So they perform the process increasingly slowly, and as they turn down the speed, they approach the theoretical limit. Maybe that seems sort of obvious that that's what needs to be done, but resource theorists aren't having this conversation. They're not thinking in this way. And I think that we should think more about how these optima results could be realized or not observed. In particular, some of the theorems are no-go theorems. I had a 2-week conversation with some people about how we might or might not be able to get around the idea of no-go to see whether we can observe it. I talked about the most popular model for a battery, the work fit. And maybe you cannot design your Hamiltonian such that it has some particular gap, such that you can tune it very, very well, such that if you calculate W, then you can create a gap of W. There are multiple questions about distance measures and error and failure. A little earlier, I introduced an epsilon to signify that our agent might not mind creating a state that's very similar but distinct from the state she really wants to create. Often we use the trace distance, but there are some signals that might not be the most suitable thermodynamic distance measure. I'm also interested in, I've tried to think about how you would observe whether this predicted epsilon is satisfied in experiment. It seems like I would have to make that epsilon in the theory work against the actual experimental precision, which is a well-defined quantity by experimentalists. So I think there needs to be more conversation about everyone's distance measures and everyone's different sorts of errors. In summary, we talked about thermodynamic resource theories, a simple model for statistical mechanics or thermodynamics at small or arbitrary scales. We talked about one-shot information theory, which is a mathematical toolkit applied in thermodynamic resource theories. what would we like to look for if we are trying to realize thermodynamic resource theories physically? We want to see interesting entropies that signal different rates or efficiencies of processes that we might expect to be the reverses of each other, but aren't actually. I argue that now is the time to realize thermodynamic resource theories physically, to have a lot of control over the platforms. These are part of the inspirations for the theory. So if the theory actually connects to these platforms, we should be applying the theory, taking advantage of it. And on the other hand, if not, when will we see these effects in experiments? And if never, should we be wasting our time with the theory, or are the fundamental limitations derived with the theory enough, and we never need to make any direct connections with the experiment? We talked about some of the questions that need to be asked to start to bridge the gap. So, thanks for your consideration.
Any questions?
Does the one-shot theory provide any insight on what the thermodynamic limit is? So it's n goes to infinity, but how fast do you converge to the n goes to infinity limit? Do you need 10 trials, 100, 1,000?
There are a lot of ways one can approach that question. I'll give what I think is the most relevant answer. So within one-shot information theory, there is a sub-branch called second-order asymptotics. People who study second-order asymptotics, which has been very popular in the past few years, study as n grows very large, but not infinitely large, at what rate do these entropies approach the Shannon entropy? So that's, and I gave the results, I showed how we would step through the n approaches infinity limit, but we could also step similarly through a second order result. And that's actually a pretty interesting result. As n grows very, very large, the work cost approaches the work yield, but always the work cost is a little bit greater by order root n. So I'll just sketch this. So the work cost is going to be something like this dimensionful energy factor, and then we'll have the relative entropy. Then there's going to be a correction term. It's of order root n. I left out the n from the other side, sorry about that. But there's also the work yield. It's approaches the same thing. There's this dimensionful energy factor. There's the relative entropy, that's the actual asymptotic rate. And then there's a minus sign with an order of roots n. This tells us as n grows very large, you're going to approach reversibility. However, you're always going to have to pay a little more work than you can extract.
Is it 1 over root n?
That would make sense.
Presumably this is the work cost for doing it n times.
It'll have to disappear. Yeah, it'll have to disappear as n approaches infinity. So, and I see that as a sort of spiritual manifestation of the second law, that you always have to pay in more than you can get out, you can never win.
So an alternative natural definition of free operations would be operations that have the Gibbs state at a fixed point. So would that be equivalent to your formulation?
Some interesting work has been done on this, in particular by Philippe Feist at ETH Zurich. So this set of free operations is relatively restricted. It always preserves the Gibbs states, but you can consider a larger set of all the operations that preserve the Gibbs state. So Philippe did a study in which he compared the two sets of operations, and maybe you're thinking of LOCC versus separability preserving operations. So he did a study, and he found that in the quasi-classical case, if everything commutes, then these two sets of operations are equivalent, but if there are coherences, then they're inequivalent. But yes, the larger set is less physically realistic probably, but easier to deal with mathematically.
Which is the larger? Sorry. The one I mentioned.
The one that you mentioned,
Okay.
rather than the one I presented.
Okay.
So for your very first proposal for your sort of theoretical experimental convergence hierarchies, you mentioned that the work restriction of the unitary in particular is something that doesn't appear to have a whole lot of experimental significance, I guess.
Maybe I should
Is there-
clarify.
well-
So in this case, I was saying that the agent can perform any energy preserving unitary for free, whereas the experimentalist might have a hard time performing some of those unitaries. So the experimentalist probably doesn't have control as good as the agent has.
Okay, so the ideal then would still be to work within the class of energy preserving unitaries, but like sort of the experimentally accessible ones,
But that's
rather than maybe generalizing it in the opposite direction and somehow like maintaining some of the semblance of the original research theory while removing the energy preserving restriction.
actually both of those possibilities could be explored and have been talked about. I just talked about the difference between the amounts of control that people had. Now, earlier during the break, we were talking about how, suppose that you have an agent who injects some work into the system, so the system of interest Hamiltonian plus back Hamiltonian is not actually conserved. Then you can always incorporate that extra source of energy into the total Hamiltonian. So it's sort of already incorporated into the resource theory. However, you could say, well, if I really wanted to write down a model for a closed system, I would have to include the entire universe.
Right, because
That
you
isn't
could be
easy.
injecting like an indeterminate amount of energy, right? If you made it.
And you have to
Yeah.
include a whole lot of subsystems.
Yeah.
So you might say instead, I know that there are some subsystems that I'm just they're never going to enter my model realistically because I can never figure out everything that's happening to my system. So you might have the unitary commuting with the total Hamiltonian to within some delta.
Okay.
That's actually been talked about very briefly at the end of one of the papers, but in a very, very limited scope. And there is opportunity to do more with it.
In quantum many-body physics, one theory that is, well, you mentioned like not all unitary are accessible. One theory that, one resource theory for when you're limited on unitary transformation is the theory of topological order, because you can say, topological phase are phase that are closed under simple unitary transformation. So, have you ever seen something where, like in thermodynamic, topological ordered state becomes a resource?
I haven't seen topological order mentioned, but sort of the only thing that comes to mind that's a bit close is the use of group theory and studying the set of unitaries. I was talking with Michael about this earlier. And also, if coherences are discussed, then people consider the unitaries in terms of groups. So maybe that's a little more relevant, but I haven't seen anyone talking about using topological language in this context, but it could be useful.
Groups is a little bit different, because a group suggests that if you can apply a gate as many times as you want. And topological order is like you can only apply a small number of gates. So it does not form a group.
Okay. That could be useful to try to pull tools in, or the way of thinking from that field. I have a feeling that John's next Twitter post is going to be like, Nicole introduces Eminem into the IQIM Seminar. Eminem debuts at the IQIM Seminar. You can take the idea, I don't mind.
Well, if there are no further questions, let's thank the speaker again. I apologize that we didn't have coffee. coffee before. They were late, but we do have it now. So have the coffee.
Yes. You like up again.